So thank you. It's really great to be here in Oslo for Elm Day. See so many great talks. Actually, this is my third time in Oslo. I came here in 1969 for a research conference in mathematics, and then I came here about 10 years ago with my father, so this is my third, but certainly not final trip. So I'd like to talk about Elm tar. It has nothing to do with people riding bicycles or sticky, gooey liquids, but rather with the Unix command tar-cvf. What is it? It's a way of taking a bunch of files, maybe some text files, some image files, whatever, putting them together into one big file, which you can download or send via email, and then the person on the other end can extract those files using tar-xvf. The origin of the name, by the way, goes back to the old days of computing when data was stored on magnetic tapes. So TAR stands for tape archive. And we'll see this ancestral history coming back several times in the talk. Why did I get involved in this? Well, I had to because there's an application I've been working on for some time. It's a content management app for things like math lecture notes, a very specialized niche product. And the problem is that authors spend a lot of time, writing documents. They consist of a bunch of LaTeX files, a bunch of image files, and they don't like to have their creative work locked up in somebody's app, even if it's a great app, okay? They need to have a way of taking it from the cloud and getting it down into their computer, maybe to work on it in some other way, or maybe just for emotional warmth, whatever, okay? So if you want to work with tar archives, you need to work at the level of binary data. And until very recently, this was not possible in Elm. You had to go through ports. You couldn't do it in Elm per se. Fortunately, our hero, Evan, recently released a fantastic package, actually a couple of them, Elm File and Elm Bytes. And so I use Elm File to do stuff with the tar archive that's eventually produced. But the critical one is this Elm Bytes package, which allows you to work directly on the level of bytes in Elm. Okay? So I think there are going to be many other things coming out of this, by the way. So on the one hand, I'm explaining to you, how I developed this package, what the challenges were. But more generally, I hope that it's an inspiration for many other people to do many other things at the byte level. So let's think about some things at the byte level. So let's look at the string Jello. So on the one hand, it's a sequence of alphabetic characters. On the other hand, it can be viewed as a sequence of ASCII codes. You can look at those ASCII codes in hexadecimal form. You can also write each of those hexadecimal pairs as a binary string, or you can concatenate those binary strings and you get a byte sequence. So this is how things are actually stored in the memory of a computer. So this is the level that the bytes package works on. Now let's look a little bit at the API for the bytes package. It's, as everything that Evan does, it's very well designed. There are two top-level functions. The first is encode, and the second is decode. So they're basically inverse functions of each other. The purpose of encode is to take data and to turn it into a byte sequence, and the purpose of decode is to do the reverse, okay? So I think of these things, they're functions, right? And functions are little machines that take data and they transform it into other data. So the encode function takes an encoder. It might be, say, an encoder for strings. And you put it in the hopper, and out at the bottom comes out a byte sequence. In this case, if you don't recognize it, it's the beginning of the byte sequence for Jello, okay? Or the decoder, that's a function that takes two inputs, some data, a byte sequence, a decoder that tells the decode function how to decode it, and out pops an Elm value, in this case, just Jello, okay? So the best way to understand how to work with these things is to experiment with them in the REPL. So I'm actually an advocate of REPL-driven programming, and we'll see an example of it here. So we first of all import the packages that we need. The bytes package and a little package I wrote called hex that just has two functions for viewing byte sequences, okay? So let's take some data, Jello. let's rig up an encoder for it. So we apply encode.string to the string jello, and that is an encoder that we can then apply the encode function to, and out pops a 5-byte sequence. Now, this is what you see in the REPL, maybe with different colors. And I like to be sure that I'm doing what I think I'm doing. So that was the purpose of the hex package. So if I apply from bytes to the byte sequence, I get 6A, 6.5, 6.6. By the way, you see 6C, 6C, so that's the repeated character LL. Okay. Anyway, that's correct. That is indeed the hexadecimal version of the ASCII code version of the string jello. So it checks out. Or, better yet, you can apply the decode function to that byte sequence using a specific decoder. So if you look in the API there's bytes.decode and there's bytes.encode. And in bytes.decode, you will find various decoders. One of them is decode.string. It takes an extra argument, which is the number of bytes that you are going to try to decode. Okay, so that's a quick introduction to the Bytes API. How do you begin on a project like this? Well, the first thing that you need to understand is what is the file format? And yes, that's what that stands for. Okay, so I looked around, I found a great reference in Wikipedia. In fact, that seemed to be the best reference around. And well, what did I learn? I first of all learned that a tar archive is a sequence of blocks. Each block is 512 bytes long. There are certain special blocks called null blocks, which are just filled with zeros. They're used to represent the end of the tape archive. Not tar archive. Going a little deeper, a tar archive is a sequence of bytes. There's one sequence for each file, so F1, F2, and so forth. And there are 2 null blocks to signify the end of the tar archive. As I perhaps alluded at the beginning, this goes back to the prehistory of things, because you had these magnetic tape readers, and when they saw 1,024 zeros going by, they said, hey, that's the end of the archive, let's do something else now. Okay, let's go a little bit deeper. So what does the byte sequence of a file f sub I look like? Well, it is now a sequence of blocks. So we're down at the block level. The first block is a header block that it consists of metadata for the file. Okay, the file name, its creation date, its length, and so forth. A checksum, very important. And that's followed by the actual data blocks. And the very last data block has to be filled up with zeros in order to make it have length 512, if need be, which it usually is. Okay, what about the header? This is actually the most complicated part of the whole business. I'm just going to talk about the first 257 bytes of the header. There's more to it. In the old days, it was filled with zeros. But then people realized in around 1988 that you couldn't represent files with very long file names, or you couldn't represent very long files because there was a limitation on the way the file size was encoded. So they added something in the remaining part of that 512 byte block to handle this, but it was done in such a way that it was compatible with the old standard. Okay, so there is a picture of that 257 bytes of data. If you look at the table, you see, for example, let's see if this little point, very good. So at field offset 0, i.e. at the beginning of the block, you have the file name, and that occupies 100 bytes. We're not going to look at all of it, but say at offset 124, there is a 12-byte field for the file size in some kind of octal encoding. And the fact that it's only 12 bytes long means that it can't be arbitrarily large. Very important, at offset 148, there's an 8-byte checksum field. You have to get that exactly right, which I definitely did not get at first. Otherwise, your tar archive will be non-extractable. Okay, let's talk a little bit about the API and the types for Elm tar. So there are 2 functions, create archive and extract archive. and they should be inverses of each other. I have to make well, let's say what these are first. So create archive takes a list of things, a list of pairs, metadata and data. So metadata has the stuff like the file name, maybe the owner's name, stuff like that, creation date. Data is the actual data, and by the way, that can be either strings or binary data. And the great thing about the Elm type system is it gives you a nice way of discriminating between those two types of data. When I first wrote the package, I only did create archive because that's what I needed. And then later I realized, you really ought to write the inverse function. But I was lazy, so I didn't do the right thing. Instead of metadata here, I just had a very small record that had the file size and the file name, and maybe the file extension for some reason. And during the practice session, Runar pointed this out to me and said, okay, yeah, that's really not quite right. But by the way, if you have this kind of asymmetry in your functions, it's almost always a sign of either bad or lazy design. So between the practice session and now I fixed that, Runar also asked me another question. He said, oh, well, what about your tests? And I said, oh dear, I don't have any tests. My testing was testing by the seat of the pants. That is to say, I was really mainly interested in create archive, so I would make an archive and then download it using Elm file, and then I would see if I could extract it and get out of it what I had put in, and yeah, it worked. Well, of course, it turned out that the create archive function was right, but the extract archive was not quite right. It was leaving some trailing nulls. It was sort of not cleaning up after itself. Okay, so let's see. I've sort of explained everything but the type of the metadata. So let's look at that. That's going to be a record that is pretty much in one-to-one correspondence with the Wikipedia table. And if I click through this, you'll see that that's not quite right. There's one thing that's missing, which is the checksum. And there's a technical reason for that, which I probably won't have time to go into here. But anyway, let's keep moving here. So the best way to actually to develop this sort of stuff and also for you to see how it works is, again, to work with it in the REPL. So let's take some data, Jello. Let's encode it as before to get some binary data. Let's cook up some metadata. So that record is sort of long and it's sort of a pain to always fill out all those fields. So I provided a convenience default metadata which you can just modify as needed. So we'll just give it a name. File name equals menu. Okay. And then you can create an archive by running the create archive function on the list of one element consisting of a single pair metadata, comma, binary data BB. So we're treating this thing as binary data now. And it checks out because this is 2048 bytes long. If you divide by 512, that's 4. So there's one block for the header, one block for the data, 2 blocks of zeros to terminate the thing. So that checks out. And you can also view it from bytes. And if you look up your things in your hex table, you'll see that this is the hexadecimal encoding of the ASCII encoding of the string menu. And you can look further into this. It checks out. Now let's do the reverse with the fixed up extract archive. Now actually this is, I fixed this about 3 a.m. this morning. You'll notice that there's something not correct here. My binary data was 5 bytes long. I made 2 mistakes. I didn't clean up in the trailing stuff I tried to in the string data version, but there's a mistake there that I still haven't figured out, and I just plain didn't do it in the binary version. Turns out to be it's very easy to do that, so I fixed that, so that really should read 5. Okay, the 12 is a misprint. Okay, so then you can, it's done correctly. I also wrote, after the practice session with Runar and his colleagues, some functions to, I don't have tests yet, but I have functions that help you to test it manually. So you can extract the binary data from for example, the 0th element in this list of pairs, and you can pipe it into hex, and you can look at, actually that's not needed now, but it checks out. You get, that's Jello right there, okay? So that is, let's see, there we go. And you can also download it and check it with a hex editor. So it all checks out now, except for this one remaining error. Well, in the remaining 4 minutes and 50 seconds, let's dive just a little bit deeper into this and see how to work at the byte level. And one can go down a very long rabbit hole in doing this. So I'm just going to go a little ways from the entrance down the rabbit hole and then stop when the time's up. So first of all, let's see how we would encode some files. So the way you work on this is you think about what you want to do, you imagine a name for it, you figure out the types for that, and then you start digging the code further and further down. So the important thing here is encode.sequence. This is a very useful function in the bytes.encode API. It's a way, an encode.sequence takes a list of encoders, and the result of running that through encode is then a concatenation of the byte sequence produced by the elements of that list of encoders. I hope that makes sense. It's a way of stringing byte sequences one after the other once they're encoded. So what does this do? Well, the first one is going to apply encode file metadata data to the file list. So if you have 17 files, you'll have 17 byte sequences coming out of that. We have to terminate by 1024 zeros, so that's what the last thing does. So that's how encode files work. Okay, okay, let's go a little further down the rabbit hole. How does encode file work? Well, that's an easy one. It simply inspects the metadata and decides whether it should hand things off to encode text file or encode binary file. So let's just do one of these, encode binary file. You're beginning to see a recurring pattern here. In the let block, or the let clause, we figure out how big the file is. And then we're going to do something very simple here. We're going to we're going to put two sequences together, the encoded metadata and the encoded data. So it sounds like we're not really doing anything, but we are. And we're almost done, thank goodness. EncodeBytes is that's the critical one. And how does it work? Well, the first thing it does is it figures out how much data there is and how much padding has to be added to the very last block. Okay, and then it again combines, in this case, two byte sequences. The first one, it seems ridiculously easy, but you see, we're already dealing with a byte sequence, so we simply have to copy that. And that's what encode.bytes does. It's kind of like the identity function on bytes. And then we need a suitable list, a suitable block of zeros, and that's what this does. So that's the EncodeBytes function. So it's really not too bad. Turns out that the decoder was a little bit more difficult to rig up. And I have deliberately omitted this slide. That's the complicated one. But notice, once again, lots of encode sequences, and then you have to do some funny octal encoding, and you have to get the checksum. So I'm going to skip rapidly past all of that stuff, and we'll go back here. It may seem, by the way, that everything went very smoothly in this project. That's not quite the case. I found the road blocked at various times, and there are various things I tried to get out of the block. One was Elm slack, one was just taking a break, but most important was the scientific method. I would prepare specimens by making a file using Elm tar. I would prepare a control specimen by running tar-cvf, and then I would compare them under the microscope, which in my case was a hex editor, and by noting the differences, I could usually figure out where I had gone wrong. So what's missing? Well, it would be very nice to have compression, say maybe in this or maybe as a separate package. I think there are many things that could be done with image manipulation. You know, flipping images, rotating, resizing them, cropping them, etc. And there are many things that can be done with audio and MIDI. So that's the end. Elm is a great language. Thank you very much.